All right. I think we're in business now.
Oh, it's you.
There I am. Okay, so this is one of the biggest units
Oh, it shoot, yeah.
Oh, yeah, I remember.
of the year. Now, in terms of the breakdown of percentages based by unit, this unit technically is the largest percentage of that exam on Friday. Now, the reason why this is considered the largest percentage of all problems on the test is because intermolecular forces apply to a whole bunch of different situations, okay? So let's talk about intermolecular forces. Let's revisit the three types that we've discussed. Let's talk about why they exist, how they exist, when they exist, and their relative strengths versus one another. Because that's really the context that this unit is kind of the big takeaway of this unit, I guess, is understanding those relationships of intermolecular forces. Good? Okay. So, without further ado, identify the strongest type of intermolecular force in each of the following. Now, what are the three types of intermolecular forces we discussed way back in the fall?
Hydrogen bond.
We've got London dispersion forces. We've got dipole forces. And we also have hydrogen bonding. Okay? All things being equal, meaning if I have three molecules that are all almost the exact same size, the rank of strongest to weakest, or weakest to strongest rather, is the way I've written it. Okay? London dispersion forces are by far the weakest intermolecular force. They occur when you have a non-polar molecule. Okay? Now, if I say the words non-polar, or if I say the word polar, you know what I mean. That's the other problem, right? What does non-polar or polar mean? I don't care which one you pick. Can you describe either one of those? Because the other one's the opposite. Sam?
Symmetrical.
Yeah, generally, yes. I'm looking for a more non-geometrically based answer. Charges? Or partial charges, I should say. Yes. In a nonpolar molecule, there's effectively no partial charges, or an even distribution of partial charges based off of symmetry, so they all cancel. Okay? So a nonpolar molecule has no regions of partial negative, partial positive. It's neutral more or less throughout. Okay? What's a polar molecule then? I've got partial charges. The poster child of a polar molecule is water. Okay? Water looks like this. It is bent. We can draw the lone pairs on there. Okay, water is a bent molecule. As a result, the oxygen is more electronegative. Sound familiar? And these bonds have electrons that are unevenly shared. And what happens is we get a partial negative charge up here and partial positive charges down here. Okay? Water is again, the poster child of what we would call a polar molecule. It's polar because it's got partial charges. The electrons are unevenly distributed. For two reasons. One, because we have a highly electronegative element with a not very electronegative element. But two, the shape is asymmetrical. Because it's bent and not linear, I can't possibly cancel those partial charges out, right? If it were linear, Well, then I would have like the oxygen in the middle, the hydrogen's coming out on either side, and it would be symmetrical, and it would be non-polar. But water being bent is part of the reason why it's polar. So polar means partial charges are on your molecule. Non-polar means perfectly symmetrical, usually, and all of those partial charges are canceled out. Now, when they use non-polar examples on Friday's exam, they're probably going to use an example of an organic molecule. If you have a molecule that is carbon and hydrogen and nothing else, it's non-polar. Okay, say that again, because it's going to show up. If you have a molecule that is only carbon and hydrogen and nothing else in the formula, it is non-polar. The shape is irrelevant. Carbons and hydrogens, nothing else, non-polar. Okay? So over here I'll make that black again to match, I guess. Okay. I don't know if I want to put that over there. Do I want to put that over there? Yeah. Okay, carbon and hydrogen molecules, basically. So if I have C3H8, it's nonpolar. If I have C4H10, it's nonpolar. Okay? Now, nonpolar substances have what type of intermolecular force? London dispersion. London dispersion forces are the weakest. But again, please remember this little nugget too. The example I used over and over and over again last fall was wax. Wax is a nonpolar molecule. Okay? Wax molecules are nonpolar. So all they have is London dispersion forces. But they're solid at room temperature, right? So do not be fooled by the trap question they're going to ask you. Things that are nonpolar and have nothing but London dispersion forces can have enough of those London dispersion forces to be solid substances at room temperature. Essentially, as the molar mass increases and the number of electrons increase, the net sum of London dispersion forces goes up and up and up and up. So when you get to these very, very, very big carbon chains, okay, like a wax molecule, huge molar mass, right? And even though it's nonpolar, and even though it's only London dispersion forces, it still can have enough intermolecular force to be a solid substance at room temperature. So this is the order. These are the weakest, these are the next, these are the strongest. But I can have a molecule with nothing but this, and if it's really, really big, it can still be solid, and it can still have strong enough forces to be a solid substance. Okay, that's kind of the trap question. They sometimes will trick you. Dipole-dipole. These happen with polar molecules. Okay? Now, hydrogen bonding is also polar molecules, but we need a special thing to also be there. Okay? So this is also polar. And you need a hydrogen covalently bonded to fluorine, oxygen, or nitrogen. Hydrogen bonding only occurs if that hydrogen in the molecule is bonded to a fluorine, an oxygen, or a nitrogen. Okay? You can only have hydrogen bonding if that is also true. So if I have hydrogen bonded to carbon, I'm not going to get hydrogen bonding. If I have hydrogens bonded to phosphorus, I'm not going to get hydrogen bonding. Hydrogen bonding as an intermolecular force can only happen if those hydrogens are covalently bonded to fluorine, oxygen, or nitrogen. What's so special about fluorine, oxygen, or nitrogen? The greatest electronegativity. Yeah. The greatest electronegativity. Those are the three most electronegative elements that exist on the periodic table. Okay? So these are the three types. This is what we got to work with. So to determine what exists in any given molecule, we have to be able to analyze it and realize, okay, is this polar or is this nonpolar? And if you can make that distinction, you can usually figure out the correct intermolecular force. If it's nonpolar, you've got London dispersion forces. If it's polar, you have at least dipole-dipole, and you might have hydrogen bonding if this special criteria is met. Okay? Something else you'd want to know. Absolutely every single thing that exists has London dispersion forces. Everything. Everything. Yes. Everything has London dispersion forces. Now, in water, the London dispersion forces are kind of irrelevant. Why? Well, because we got a stronger type of force existing, right? Hydrogen bonds between water molecules are way the heck stronger than the London dispersion forces between water molecules. So the London dispersion forces in water are, who cares? I mean, really, they don't affect a thing, really, because we have a stronger type of intermolecular force present. So the London dispersion forces matter the most when they're the only type that exists. Sam?
Do you think there'll be questions on the AP test about like what it means when there's like stronger forces? Like what will that do to the molecule?
Yes. 100%. So let me segue into that. What do they ask you when they ask you intermolecular forces questions? They generally will never use the word intermolecular force. They hide it. For example, okay, so we'll go IMF questions. Okay, what do they ask? They ask about boiling point. That's their favorite. If you see a boiling point question, it's an intermolecular forces question. If they ask about the boiling point or want you to compare boiling points of two different things, it's an intermolecular forces question, guaranteed, dead giveaway. Their other favorite one is vapor pressure. Okay, these are the two they generally like to use. However, we could use the other phase change. Okay. Melting freezing point. But when they ask questions about intermolecular forces, they're probably going to use one of these three things. The fourth that they would maybe use, I don't think that I've seen it in a while, but in theory, they could also ask about viscosity. Okay. Yeah, okay, so let me give you a very real life example. I have water and I have maple syrup. Which of those has stronger intermolecular forces? Yes.
Unless it's really water.
Well, gross. So, but I don't want to put it on my pancakes.
Is it even syrup now?
I don't know.
Maybe just have it.
But you get my point, right? So more viscous, meaning like thicker liquid, slower flowing liquid, has stronger intermolecular forces. Boiling point. Higher the boiling point, that means it's harder to boil. So what does that tell me about the intermolecular forces? They're stronger. The thing is being held more tightly to itself, right? If it's easier to boil a substance, that means it's easy to break those intermolecular forces. They must be weak. Vapor pressure, this is the weird one. Vapor pressure in terms of intermolecular forces is counterintuitive a little bit. Here's what vapor pressure is. Vapor pressure is if I have a liquid in a sealed container, some of those liquid molecules will just escape and turn into gas molecules. And the vapor or the gas in that sealed container exerts a pressure. If my intermolecular forces are really, really high, my vapor pressure is going to be really, really low. because they're strongly attracted to one another and they're going to stay in the liquid phase. On the opposite side of that, if I have a molecule or a substance with weaker intermolecular forces, it turns into a gas more easily, meaning the vapor pressure is high. So high vapor pressure means low intermolecular force. Low vapor pressure means high intermolecular force. Okay? This is where they're going to go. There will be questions talking about boiling point, and they want you to make a comparison of intermolecular force. There's going to be a question about vapor pressure, and they want you to make a comparison of intermolecular force. Okay? So whenever one of these words shows up, it's an intermolecular forces question. And we've got to make a comparison. Why does that have a higher boiling point than this? Okay, well that has a higher boiling point than this because that has hydrogen bonding and this is just London dispersion. Or that has a higher boiling point than this because this is London dispersion and that's London dispersion, but that one's bigger and it's got more molecules and it's got more mass and it's got more electrons. Things that are bigger or have more electrons, those are said to be more polarizable. Remember that word? Polarizability. That means more stuff, okay? More electrons. All right, let's actually do a problem. How's that sound? 20 minutes in. Good job, teacher. We can go through all of these if we want. A lot of these are more molecular geometry based than they are like, just simple things like this. Let me pick out a couple of the low-hanging fruit. Water is the poster child in H bonding. By the way, if you write hydrogen bonding in a sentence in the free response section, I would recommend you write out the whole word of hydrogen. I don't think they would be mean about that, but nonetheless, be complete in your sentences. Something else that's a low-hanging fruit. Let's see. C4H10. What kind of intermolecular force would this have?
Oh, yeah.
London dispersion forces. Nonpolar. CH4. London dispersion. Again, if you see anything with a formula of carbon, hydrogen, nothing else, it's only going to be nonpolar. It's going to be London dispersion. What else could we pick out? Carbon monoxide. That's nice and easy, I think. I've got a carbon. I've got an oxygen. Actually, sorry. I forget, but is that a double bonded? That'll be double bonded, I think. Doesn't matter. Even if it's single bonded, who cares? I've got a carbon, I've got an oxygen. Polar or non-polar?
Polar.
Yeah, why? Oxygen is more electronegative, meaning these electrons are not equally shared, right? They're being pulled in that direction. So if this is polar, what kind of intermolecular force would this have? Dipole-dipole. Why is it not hydrogen bonding? Yeah, there's literally no hydrogen, so that's kind of a dead giveaway. Good job, everybody.
Thank you.
Okay. Like I said, some of these are kind of relying upon like shape and geometry. They're not really going to do that to you, I don't think. Chlorine. What? Oh. Chlorine. Yeah. HF? Yeah, okay, good. Now, again, this is polar. And we've met the special criteria, right? Hydrogen is covalently bonded to a fluorine. Okay, this must be H bonding. Okay, you can look at all those, right? You can go online, you can find all those. This one's a dumb one. I put an ionic compound in here. This one's a dumb one. I put an ionic compound in here. Ionic compounds are, ionic. Okay. Ionic bonds are technically intramolecular forces. They're like, bonds, actual bonds. Remember that intermolecular forces are simply just attractions between our molecules. I think we're okay here now, right? Yes, maybe? I want to keep going. I'm sorry. That was very long-winded, but I think it's been a hot second on intermolecular forces.
Yeah.
Is that helpful?
Very.
Yeah.
Ring a bell?
Sure.
asking about boiling point. But what am I actually asking about?
Which has the strongest and weakest?
It's an intermolecular forces question. Again, if you see these words, it's a dead giveaway that they want intermolecular forces. That's what they want you to talk about. Which of these is going to have the highest boiling point?
Probably the HF. Oh. I didn't even see the name.
Why is it that one? Yeah, I mean, now, if they want an explanation, right, because they might, if this magically showed up in the free response section and they want like a legit science explanation, correct, you should say something along the lines of, all 3 molecules are nonpolar, all 3 molecules have London dispersion forces. C3H8 would have the greatest London dispersion forces due to having the greatest polarizability. Sounds fancy, but what that means is it has more electrons. Okay, so more electrons, bigger molecule means those electrons can be pushed and smushed and moved to a greater extent, which leads to bigger partial charges, which leads to stronger intermolecular forces. How about the second set? Which of these is going to have the strongest intermolecular, which of these is going to have the highest boiling point? Let's try that. Why? Hydrogen bonding. What about this one? What would it have? Dipole-dipole. It's polar, totally polar, right? If I had an H and I had a Cl, this would be partially negative, that would be partially positive. So it's definitely polar. But we didn't meet the other part of hydrogen bonding, right? The other special part of hydrogen bonding is it needs to be FON. So that's dipole-dipole. This is dipole-dipole. That's H bonding, and that's why it wins. Okay, these are the types of questions you can expect to see. Types of solids, I don't think I care. I don't think AP cares. What they might ask you is a properties question on the types of solids. That's generally where they go. And what you need to know is metals. Okay, things like gold and tungsten. Do I have any other metals? No, only those 2. What is special about metallic substances? They conduct electricity. What's true about valence electrons in a metallic sample? It's a sea of electrons. They're free-flowing throughout the sample. What else can I do with 2 different metals? I can make an alloy. What kind of alloys exist? There's 2 types. Substitutional and interstitial. We've been hanging out. Unfortunately, chromatics, I'm like her best friend recently. It's not great, I'm sorry.
It's okay.
There's got to be better
Like, no, are
people.
you suck?
There's got to be better people to hang out with. That's what I'm saying.
I should not. As far as like teaching go, I think it's well.
All right, I appreciate that. Thanks, David. Oof.
We're just throwing.
Do I need to shut the door? We're close by. Careful. Okay, so metals, high conductivity. Okay, they are malleable, meaning I can like shape and mold them. Okay, they have a sea of valence electrons. That's generally what they're going to ask you for with metals. Okay, high melting points for the most part, right? Generally have high melting points. Let's talk about the other type that they usually go to, and that's ionic. Okay, so this is metallic. Ionic. Let's talk about the properties of ionic substances. Melting point,
Super.
really high. Do they conduct electricity?
Nope, wind no.
Yes, we gotta be careful. In the solid form, ionic compounds do not conduct electricity. If I dissolve them in water, well then I've separated the ions, right?
Yes.
When you dissolve a salt solution or an ionic compound in water, you're breaking it apart and now you have ions. Yeah, it's going to conduct electricity. The other way you can make it conduct electricity is if you melt it. Molten ionic compounds also conduct electricity. Okay? So, high melting points, they're brittle. That's the other term that they like to use with ionic compounds, because they cleave really easily. You can take a grain of salt and smash it right into smaller grains of salt without too much trouble. Okay. And then maybe if they're feeling extra fancy, they might go to the covalent networks. Oops. These are both covalent network, the top two. Covalent networks are quite literally a network of covalent bonds in all three dimensions. Graphite, diamond, and silicon dioxide are the three examples they use. Graphite is pure carbon, diamond is pure carbon, silicon dioxide is glass or quartz. Okay? These are examples of covalently bonded solid structures. What properties would that have? What's the melting point of diamond?
Very, very high.
Insanely high. These are hard substances. Very high melting point. Okay? Abrasive. They are strong three-dimensional covalent structures. Okay? And I think that's all they would ever talk about. Silicon dioxide melts at a very high temp because it is a covalent network. I think I filled this one in for you, right? There was blanks. Whereas carbon dioxide melts at a lower temperature because it is a molecular solid with London dispersion, intermolecular forces of attraction. A couple different little things they could maybe ask, right? If you look at those formulas, I have SiO2 versus CO2. Very, very similar. Carbon and silicon are even in the same family on the periodic table. But this is glass, and that's like, gas. Okay. What do I need to do here?
This is a lot of.
Yeah, it is. What is the total pressure in a 15-liter tank if I have 523 grams at 25 degrees Celsius? Okay, what have they given me? Volume, temperature.
Yeah.
This is grams, but I can certainly convert that to moles without too much trouble, right? So we'll say that this is N. And what do I want to solve for? Pressure. So what do I need to use?
You have to convert the temperature.
100%. Yes. Remember, when we're using temperatures in any of our calculations, unless it is delta T, meaning change in temperature, final minus initial, we must be using Kelvin. Okay? So the only time you're really allowed to leave your temperature the way it is in Celsius is if you're using Q equals MC delta T, which is a thermodynamic equation for solving for the amount of heat transfer. Okay? I don't think I need to do this. This is pretty easy math. I like your chances. And maybe the hard part's getting to there, but once you realize it's that, I think it's pretty pluggy and chuggy.
I've come across questions where it's like you had 6 liters of one gas and 10 of another, and then it's pumped into a 4-liter tank. What's the pressure?
Yeah.
How do you go about? Would you solve for what? For each
So gases. We also have an equation like. No, the type of gas doesn't matter. Here's what I'll say. We have an equation in your packet that looks like this, right? Where the total pressure equals the partial pressure of A plus the partial pressure of B plus the partial pressure of C and blah, blah, blah. Okay? Long story short, each gas will behave the exact same way. If I have a mixture of hydrogen and oxygen and water vapor, all that really matters if I want the total pressure is that I have the total moles. Because they'll all behave similarly. All gases occupy the same volume under the same conditions. Okay? So depending upon the context, I don't think I've talked to you about that one yet, but depending upon the context, the total pressure of your system is just the pressures of those gases added up. If I want to solve for the total pressure of a mixture of gas, well, if I get the total moles, well, then I'm good to go. Okay? On the contrary of that, if I want a partial pressure, I can just use the ratio between my gases. Okay? Let's say I have 6 moles of oxygen and 4 moles of hydrogen, and the total pressure is 10. say that again. I have a total pressure of 10 atmospheres. 6 moles are oxygen, 4 moles are hydrogen. What's the partial pressure of oxygen? Oh, sorry, I said 6, didn't I? This is what happens when you make up problems on the spot. Total pressure is 10 atmospheres. I've got 6 moles of oxygen, 4 moles of hydrogen. What's the partial pressure of oxygen? Don't overthink it. Yeah, literally, okay? So this would be P of oxygen, the partial pressure of oxygen would be 6. And the partial pressure of hydrogen would be 4. The mole ratio of gases matches the pressure ratio of gases. I don't know if I helped.
I think you would.
If you find it, we can certainly talk about it later. Oh, by the way, if you're free after school, so am I. Both tomorrow, today and tomorrow. If you want to hang out after school and do some chem and you're free and you want to chill, please hang out. I would love to help you. That sounds great. A tank contains 1.23 moles of argon, 0.87 moles of oxygen, and 0.55 moles of nitrogen. If the total pressure in the tank is 5.44 atmospheres, I should have just switched slides, huh?
Yes.
Maybe.
Pro tip. Don't make up a problem on the spot. Go to the next slide and you probably have it. Okay. Yeah, this is literally what I was just doing, right? That's the total pressure. What's the ratio of moles of the oxygen, and that's going to give you your pressure of oxygen. Mole ratios and pressure ratios are the same. It's basically the moral of that story. What else we got? Another PV equals nRT? No, not quite. Well, sort of. Yeah, we just added them together. I was talking about this too. So I have 5.5 moles of gas. I would use that for N, 10 liters, 20 degrees Celsius. I would switch that to Kelvin, but yeah, PV equals nRT once more. Which of the following gases is said to be the most ideal? Because we call that equation the ideal gas law, right? What does that word mean? Remember, what is an ideal gas? Correct. An ideal gas is a gas with 0 intermolecular forces. Does that actually exist? No. But in reality, remember, your gas particles are separated, right? There's space between them. So even if they have intermolecular forces, they are going to be weak, right? There's a reason why it's a gas. Gases are in the gaseous phase because they have weak intermolecular forces. However, there still is some attraction there. Not much, but there still is a little bit. And an ideal gas is one with no intermolecular forces. So what am I really asking? I'm really asking which of these has the absolute weakest intermolecular forces of attraction. Now, this is polar, dipole-dipole. That's kind of strong for a gas. This is nonpolar, London dispersion, nonpolar, London dispersion, nonpolar, London dispersion. Why that one? That one is the least polarizable. It has the fewest number of electrons. It has the lowest molar mass. It's the smallest. The smaller a molecule, the less electrons that molecule or atom has, the less polarizable it is, and meaning the less London dispersion forces it has. This is the most ideal, okay? Going quick. Ooh, fun. These are good questions.
I agree.
You have an equation in here that we probably never solved for unless you've taken physics. Kinetic energy equals 1/2 mass times velocity squared. As the mass of a gas particle goes up, what must happen to the velocity of that gas particle in order for the kinetic energy to remain constant? Goes down. We have an inverse relationship. Very, very light gas particles with low molar masses are moving really, really fast at the same temperature of other gases, right? So that's the takeaway here. What temperature is temperature is the average kinetic energy of a sample. So if I have two gases at the same temperature, I have the same kinetic energy. So if all of these are at the same temp, they all have the same kinetic energy, and now I can figure out which one's moving the fastest. Big mass, slow velocity. Low mass, tiny mass, big velocity. So which of them are moving the fastest? Well, I want the lightest particles. I'm going to look up their molar masses. Molar mass of CO2 is 44. Molar mass of xenon is something. What is it? $131? Pretty big. 44, 131. Molar mass of this is 16. Molar mass of helium is 4. Smallest mass, which one's moving the fastest? This guy. Hey, look, pictures. What ionic compound could this possibly represent? Sure. Are there others? Sure. As long as it's 1 plus 1 minus, you're good. What ionic compound could this represent? Sodium oxide. Sure. I just need a 2 minus 1 plus, right? Sodium sulfate. We could use a polyatomic ion if we're feeling fancy. That's all this is. If you see a picture, don't overthink it. By the way, if you see a picture on the AP test, count. Again, if you've done practice materials, you know this by now, but they love just making you count things. It's like, oh, look, I have 8, and now I have 4. How many moles of product did I make if I started with 2 moles of reactant? I made 1 mole because I have half of what I had over there. Okay, be prepared to like count stupid pictures. Sorry, fun pictures. Ooh, chromatography.
It's like exciting.
It's been a while. It's exciting stuff, Luca.
Oh, yeah, it's so
Dylan?
Do you look over what you're teaching before you get?
Clearly not.
No.
Because look at how excited he gets every time.
No.
What's freaking
Hey,
going on?
okay, so we're gonna get these slides back. Oh, yeah, Dylan walked a long time ago.
Oh, yeah, I should have just changed the slide.
Yeah, we realize this by now. No, I show up and I teach things.
So did you make these slides like once when you first started teaching class and you just never bothered?
I made this last year. Specifically, this was made
You don't
last year.
remember this one?
Well, it's been a year.
Really? Come on. I don't teach the lights.
It's more fun. I like.
Oh,
Yeah.
that's it.
All right, so this is chromatography. Let's talk about this a little bit. Chromatography is pretty darn simple. We okay up there? You're just ripping on me as a teacher? Oh, okay. I mean, it's okay if you are. I respect it.
What does it say?
Well, that's rude.
I didn't write it.
What does it say?
What does
I can't see it from here.
Mr. B is like he had.
The headset.
Oh,
That's so mean.
that was I would just
Then
quit.
they put a
I
smiley
would just
face
walk
on
out
it.
if I were you, just leave.
I don't know, so passive aggressive. Yeah.
I don't care. Okay,
It doesn't
so
erase it, just-
chromatography. I don't care. Chromatography involves a piece of paper or a piece of what's called a plate. A TLC plate is what it would be called, but don't worry about that. Basically, there are two phases. We have what's known as a stationary phase and a mobile phase. Okay? I put a little dot on the bottom of this paper. I put it inside this beaker, and the paper is just resting in the liquid at the very bottom. The liquid then, the mobile phase, will wick up the paper, and as it does so, it will take this little spot, this chemical, with it. And in theory, it should separate that chemical into two components. Okay, so this is like a before and an after picture. This is how I set it up. I put this piece of paper, I had my sample, I put the sample right there, I made a dot, I put it in the chamber, beaker, the reaction chamber, whatever you want to call it. And then as the liquid was wicking up the page, it took this little spot with it. And that spot began to separate into two different components. Okay? So the question is, which of these, no, I'm sorry, I don't want to answer that yet. Which of these two components in the mixture is more nonpolar? So let's think about intermolecular forces. The mobile phase is hexane, polar or nonpolar? Nonpolar. Carbons and hydrogens, nothing else. That's nonpolar. Now, polar things are generally attracted to other polar things. Polar substances will mix with other polar substances. Nonpolar substances will mix with other nonpolar substances. So as the hexane is wicking up the page, whatever is more attracted to the hexane will travel farther. It's attracted to the liquid. As the liquid travels and moves, the part that is most attracted to it will move farther. Okay? So, which of these is more nonpolar? X. I agree. It traveled further. And hexane, the mobile phase, is nonpolar. This must be a nonpolar substance that is attracted to the nonpolar substance that we have in the reaction chamber. Which means that component Y must be more polar, because it didn't travel as far. It's less attracted to the hexane. Okay? This is an intermolecular forces thing. The last part of chromatography is called the RF value. This means retention factor. Okay? All that is like a ratio of how far it traveled. So for example, let's say my hexane started right there and my hexane ended right up there. The RF value of this would be the distance it traveled divided by the distance that the total liquid traveled. So it's a ratio or a percentage, basically. They don't usually ask about that. What else we got? Which is more soluble in water, hexane or ethanol? You should know this. Polar things mix with polar things. Non-polar things mix with non-polar things. Here's your choices. Hexane, ethanol. Which of those is going to mix better with water? Why? Ethanol is polar. How do I know it's polar? If I have C's and H's and nothing else, it's nonpolar, right? So the hexane is nonpolar. But how do I know ethanol is polar? That's a decent question. That guy. Oxygen, very electronegative. Very, very electronegative. If you slap an oxygen in the middle of a carbon chain or on the end of a carbon chain, that oxygen is very electronegative and going to pull electrons towards itself. It's going to make your formerly nonpolar molecule, right? Previously nonpolar molecule with carbons and hydrogens and nothing else. You put an oxygen on there, it's going to be polar. Oxygen is a dead giveaway that you have a polar substance. So which of these is going to mix with water? Well, the ethanol is going to mix way better with the water. Ethanol is polar. Water is polar. Polar things mix with polar things. Like dissolves like is the phrase. If I have a nonpolar substance, it's going to dissolve better in a nonpolar solvent. Yep. Water's polar, oil's nonpolar. Okay? Polar mixes with polar, nonpolar mixes with nonpolar. If you mix them together, it doesn't go so hot. Now, why do polar things not mix with nonpolar things? Are there attractive forces between them? A little,
But not really.
teeny bit, but the polar substance is just way more attracted to itself. The reason why oil and water separate is because the water has such stronger forces of attraction to itself, so it sticks together. And the oil basically can't work its way in. The water is just too strongly attracted to itself, so it just pushes the oil off to the side more or less, you can think of it as. But there still is attractive forces between the oil and the water. They're just weaker than the attractive forces between water and itself. Sam?
Does oil have a lower viscosity than water?
Not necessarily.
What I thought-
I know, right?
Confused.
I know. So oils, the net sum of all the London dispersion forces could very well be greater than the hydrogen bonding in water. Meaning their viscosity would be higher, their boiling point would be higher than water. And generally oils do have higher boiling points than water. But the reason why water sticks to itself and not to oil is because of the partial charges, because polar, nonpolar. So kind of two different things-ish, but related. Which of the following substances would mix best with octane? Octane, polar, nonpolar. Nonpolar, what am I looking for? What do I want to mix with it then? Something nonpolar. Now, to figure out whether these are polar or not, we would have to do like a geometry, three-dimensional thinking. NH3 has a lone pair. It's trigonal pyramid. SF5 has a lone pair. This would be like a square pyramid. Oops, that's F, whatever. F polar. CF4, tetrahedral. Polar, nonpolar. Nonpolar. Polar, polar, nonpolar, polar. That's our guy. Like dissolves like, polar mixes with polar, nonpolar mixes with nonpolar. I need more hours in the day. This one I've seen show up once and never again. I don't think it's going to show up. We are now crossing over into photons. You have two equations. No, don't freak out on me. This ain't bad. The concept feels like it wants to be difficult, but this is very, very easy math. When they make you do photon math or math involving light, you've got two equations. They are the very first two equations listed on your formula packet. E equals h nu, and C equals lambda nu. E is energy, H is Planck's constant, nu is the frequency. Frequency is measured in hertz. If I multiply Planck's constant or Planck's constant by the frequency, I get the total energy of my photon, that packet of light. C is the speed of light. If I multiply the wavelength by the frequency, I get the speed of light. Speed of light is a constant. It's given to you in here. Both H and C are provided for you in your packet. And basically, it's just easy math. If I want to solve for the wavelength and I have a frequency, I would use C equals lambda nu. This is a constant in my packet. This is the frequency. I would solve for the wavelength. This turns into easy algebra stuff. Yes?
What's the label?
Wavelength is generally in nanometers. It's a distance. So it could be meters, any prefix of the base unit of meter. Most of the time it's nanometers because visible light is nanometers. If you've done any of the practice tests, how many of these questions have you come across? Yeah, I mean, literally, they're not really there. Okay, they're not really there. It's all fair game. Ooh, Beer-Lambert law. If you see anything about absorbance and concentration, this is Beer-Lambert. We have an equation for that in your packet. Second set of equations. A equals EDC. Absorbance equals molar absorptivity multiplied by the path length times the concentration. This turns into easy algebra 2. How are they going to use this in context? What you need to understand that as concentration increases, absorbance increases. Direct relationship. Okay? Sorry, this is very dense, I know. I'm just kind of throwing more crap at you. All these little tidbits of knowledge, hopefully something sticks. You can sanitize, have a lovely day. Hang in there, folks. If you want to hang out after school, I am here. Please come hang out. Sounds like fun.
Too.